All right, so this is going to be a very abbreviated version of what it was we did in class earlier this week. What was it, March 3rd and March 2nd, talking about electric fields and how they relate to what we've been doing so far. Actually, there's a lot of overlap to previous units, gravity specifically, in terms of these ideas of fields and how we use these ideas of fields in terms of our calculations. So there are two equations that we're going to start with, and together, using those two, we'll derive something that we are going to use, actually, that I want you to put on your cover page. We'll derive this together, and I want you guys to use that equation as an alternative for calculating how strong an electric field can be at whatever position it is you're at. So the first of the two equations that we're dealing with is Coulomb's law. Coulomb's law calculates the force of electrostatic attraction or repulsion. It was the one that we used in the Gizmo, the online lab that you guys worked on, or, I mean, honestly, the one that was the primary focus of all of assignment 4. It is that force of electrostatic attraction or repulsion being compared to the two charges, charge 1 or charge 2, doesn't matter, that are involved in creating that force, because we know opposites attract and like charges repel one another, and for that attraction or repulsion to take place, there has to be some sort of force. So it's based on the strength of those two charges and the distance between them. And using this particular equation in conjunction with an equation that we talked about when we did our Van de Graaff generator demonstrations, we can also move particles like the Rice Krispies or, I don't know, what were some of the other things that we were moving, the strips of paper or your hair on your head, whatever. We can cause things to move simply by them being in an electric field and responding to that electric field. So the first equation, Coulomb's law, is all about the force you would get with two charged particles. In the second equation for electric field, the one on your cover page, is all about how much force would be applied on a charge, on that value of Q, based on the strength of the electric field at that location. And so I'm going to label that second Q, Q2. Again, this is a subscript. I'm not squaring, sorry, that charge. But one of the things we can do, very similar to what we did last semester, honestly, in our gravity unit, was in October, we had Newton's second law. And we used that since it was our introduction to forces, talking about how forces cause accelerations. Things don't speed up or slow down without some sort of force being applied to it. And we got specific in that equation. We said, well, we could even use this to find the weight of an object. The force of gravity acting on an object is Newton's second law. You're just using a very specific acceleration, the acceleration due to gravity here on Earth at that particular altitude. We usually just use 10. What was it, 2 units later, when we introduced this in gravitation, universal gravitation, Newton came along a few years later and also stated that there was a gravitational attraction, a force of gravity holding all the planets in orbit around one another, and those planets orbit one another following this basic generic observation. It was the force of gravity between 2 points, or proportional to the 2 masses involved divided by the distance between them. And you'll notice that equation is remarkably similar already to Coulomb's law. They really do just follow the same observable patterns, which is really kind of cool. Well, what we did last semester, the reason I'm bringing this up, is those are 2 different ways of calculating an object's weight, the force of gravity between 2 objects. And they should give you the exact same value for weight. They do, and because we can set them equal to each other, or because they give us the same value, we can set them equal to each other. And one of the things you noticed from last semester was that the smaller mass always canceled. When we wanted to calculate the gravitational field strength of a planet, like we did in our last lab of the year, all you needed was the mass of the planet, the mass of the thing making the gravitational field, and your distance away from it. And that's exactly what we're going to see here. This, let me highlight it. This force and this force do work out to be the same thing, right? We can calculate the amount of force that one particle will exert on another particle based on their difference or their distance away from one another, or we can calculate the force that a particle feels based on its position in an electric field established by another particle. There are 2 ways of calculating the same force. And so if we set both of them equal to one another, like we did last year in gravitation, what we can do is rearrange the bottom equation, multiply both sides by Q to get that over there, and set it equal to Coulomb's law. KQ1 multiplied by Q2 divided by R squared, right? This was Q2. I just picked one of them. That way you could see that just like the smaller mass canceled out in last unit in December, in this case, March, you still have the smaller charge canceling out. And what you get from this is an equation that you should, number one, put on your equation card or cover page that describes the electric field strength the strength of a field, the strength of an electric field given some universal constant, just like we had G, and the strength of a charge that created that field and your distance away. So our equation for the strength of an electric field is proportional to some universal constant, the charge that made it, divided by how far away you are, just like gravitational fields were equal to a universal constant, the mass that established that field, divided by how far away you were from that. And that's what this new equation is and what it's meant to be. So the 2 and 3 were really just meant to help you if you struggled with assignment 4, number 3, was where we started seeing that factor of change stuff pop up again from gravitation last semester. And we're just looking at the equation. If we're looking at our electrical field strength equation, our new one that we just derived, and we want to look at the strength of an electric field as it compares to your distance away from that field, or distance away from the center of that field, I should say. We're comparing these two things. The analogy I made was to, because E's, K's, and Q's, and R's don't mean anything to us, most of us, right? So the comparison I like to make to this was the number of slices you're going to get is equal to the total amount of pizza that was made divided by the number of people in your home who are going to eat that pizza, right? This is an equation that describes the exact same sort of relationship we're going to talk about right now with electric field strength and distance. We've all done this, right? If you've got, currently in my home, there are 3 people. There's me, my wife, my daughter. And if I were to make a pizza, cut it up into 6 slices and look at that and split things up equally, each one of us are going to get 2 slices. There's 6 total slices of pizza, 3 people, 6 divided by 3 means we each get 2 slices. We have been doing this math, maybe not with slices of pizza, maybe it was pie or cookie cake or who knows, doesn't matter, right? The number of sandwiches or this number of slices of bread you've got left. It doesn't matter. I like to use this comparison with food because the idea gets across a little bit more easily than with E's and R's. So if I am home alone by myself and I decide to put a pizza in the oven, I am dividing that pizza by 1 person. I get the whole thing to myself. I get all of the slices. If it's just me and my spouse at home, now I'm dividing that amongst twice as many people, and I get exactly half the number of slices, right? The more people that are there, the less you get. We've all had that feeling when your siblings invited their friends over for dinner and you get mildly annoyed because now there's less food for you at dinner, right? Because you've got to split it amongst even more people now. It's the same idea. And so this relationship is referred to as inversely proportional. But it's not just any inversely proportional relationship. If I have twice as many people, I get half the pizza. If I have 4 times as many people, I get a quarter of the amount of pizza. That's inversely proportional. This is inversely proportional to the square of the distance between the two of them. So it's inversely proportional to the square, which means if I triple the number of people eating my pizza, I don't get 1/3 the amount of pizza. I get 1/9 the amount of pizza because I have to square that number, right? It's still inverse, which means it's still a fraction, but I have to square it. And that's what the inverse square law is, right? We talked about this with, we could have talked about it with, and that's what assignment 3 was, really. Coulomb's law. And we did definitely go over, this was on the exams for universal gravitation because it too was divided by a radius squared. It's the same inverse square law that we talked about before. So I think pizza is a little bit easier to see that with, especially when we do the next part, right? Same equation. E is equal to KQ over R squared. And in this one, I'm comparing electric field strength, which is E, to the charge And because that charge is in the numerator, or the amount of pizza that I made was in the numerator, if I double the amount of pizza that is there, I get twice as many slices. Everyone gets twice as much, right? That's really the idea here. So this is a representation of a directly proportional relationship. And this was, honestly, this goes all the way back to our first reading note quiz, our first exam. These relationships are things that we've been talking about all year, and that's all they've ever been. Directly proportional relationships. As one value gets larger, the other value also gets larger, right? If I make more pizzas, I get more pizza proportionally. And inversely proportional relationship is that if you make more pizza, or sorry, if you invite more people, you get less pizza. That's what an inversely proportional relationship was. So that was really all that we needed there. Number 4 is meant to be a quick application of it. So if you guys are trying this, give it a shot. And if you've got questions on it, take photos and send them to me. I will happily look that over and give you some pointers for number 4. But we'll see this inversely proportional. Proportional reasoning is really all this is. We'll see more of this in the review guide and later in the year, honestly. So if you've got questions or concerns, as always, don't hesitate to reach out.